Good morning, students, and welcome to week 13 of astronomy. This is a brief introduction to the concepts covered in this week and also important reminders of some of the assignments and stuff that we have to do. So let me share with you the screen. Okay, again, we are in week 13 of the astronomy. I'm going to talk about the objectives basically for this course. I'm going to actually delve into a little bit of content for this week. So it's important that we have that. And also one of the things that we're going to see is the discussion item in here, okay? The units are covered that are units 59, 60, and 62. It is important that you guys turn in the surveys. So I'm going to ask you again, I'm going to probably send you several messages from now on toward the probably the end of the month. So I'm hoping that you guys will take care of the survey as soon as possible. Please only fill it out once, okay? And we also have an exam. We have exam 2 or midterm 2 that is next week on Tuesday, November 16th. So everybody really need to be ready for this one. And again, I probably will be sending you reminders. If you don't complete the review, please take care of this review. Take care of it as soon as possible. You don't want to wait until the last day, which is Monday, actually, when this review is due, the 15th. So please take care of it and prepare yourself for the actual midterm. It's only 131 questions to go through and understand the units that are covered, unit 22, 23, 24, 25, 39, 41, 47, 48, 49, 51, 52, and 53, and the units that are mentioned in here in this week. Again, the content is in here. Let me delve quickly into the discussion here to see how it's structured this time around. The questions are actually here, so you don't need to go through the recording if you don't want to. But since you are in here, you probably are already in the recording. So the recording is going to be here. Some of the interesting videos are actually here too for how the life cycle of the low mass star is. But the question itself has to do with that topic. So you're going to basically summarize the process on how a low mass star and a high mass star go through their entire life, from when they are born to when they die, okay? And then also describe their evolution on the HR diagram. I'm going to talk about the HR diagram because this is really an important part of this week. So let's talk about the content. Please don't forget these two assignments. They're extremely important. The second one is graded. It's an important one. Yes, this one is probably not graded. Oh, it is graded, 20 points. Okay, so it's please take care of them, okay? So let me go into the content. Okay. Again, the topic for this week is going to be dealing with the HR diagram. I'm waiting for the picture to load in here. Finally, it did. The HR diagram and the life cycle of a star. Okay, so this is the topic in here. And some of the calculations that are involved is for the luminosity of the star versus the mass of the star. And also another calculation down in there. So those are, expect the assignments to be related to this ones in here. And that is the time for, or the lifetime basically of a star, how long it's going to live. Use this formula for that, okay? So those are the two main things in terms of numerical applications. In terms of concepts, it's a very, very important one is this HR diagram. The HR stands for Hertzsprung Russell, the people who developed it. And there are actually different diagrams. This is one of them that we're going to be using in this class. The HR diagram in a nutshell is how the luminosity of the star is compared to its temperature. So your independent variable is the luminosity, your independent variable is actually the temperature, surface temperature, and your dependent variable in this case is the luminosity. Okay. Stars are classified depending on their temperature and their brightness, if you wish, using this letters. So don't ask me exactly how this came out to be, because the details are actually in the book. into how they came out to be. So they are not ranked from in alphabetical order in this fashion, but they are ranked in terms of their luminosity. Again, O, B, A, F, G, that's where the sun is, K and M. There are all kinds of ways to remember it. One of them is O, B, A, fine girl, and kiss me, okay? So that's one way of remembering this. Again, so if you hear and read about a star of classification, oh, you know, it's extremely hot, okay, temperature, hot star, and a B, which is a large group of stars, it's the second one in terms of its surface temperature and so on and so forth. The sun is about 5,500 Kelvin, which puts it just in the G group, okay? Proxima, for example, is an M star because of its surface temperature, okay? So one thing to remember about the y-axis first, the luminosity, it's in logarithmic scale, where the 1 is the sun. Anything below the sun is less luminous than the sun. By a factor of 10, then by a factor of 100, by a factor of 1,000, and by a factor of 10,000, and potentially even less than that, okay? Like some dots in here that you can see in here. Extremely dim, you cannot see them. You have to have some powerful technology to really see these stars. And then you have brighter than that. You have 10, 100,000, 10,000, 100,000, and a million times brighter than the sun. So Betelgeuse is almost 100,000 times brighter than the sun, okay? Antares, which is not too far from Betelgeuse, also is extremely bright. Aldebaran also, and so on and so forth. Okay, so those are the stars. Rigel is somewhere in here, okay? Rigel and Betelgeuse are part of the Orion constellation. And then you have the nearest star, Proxima, which is about 1,000 times less than bright than the sun. This is our nearest neighbor. Okay. So again, these are the stars according to the temperature. The thing to remember about this is the brightness, the luminosity, I'm sorry. The brightness and luminosity are related to one another. Brightness is the actual apparent one, and the luminosity is the intrinsic value of the same thing. The temperature is actually not in increasing values. This is not the lowest temperature. This is actually the highest temperature, and it goes down as you move into the x-axis. This is typically backward when we do x-axis. Usually we start with small values and we increase. This one is backward, that's all. Okay, what are the characteristics of the HR diagram in terms of stars? Most of them, they live in this line, the diagonal, going from the extremely hot, extremely bright, to a very low temperature stars, very low dim stars. So this line in here is called the main sequence stars. Most of the stars live in this line. The sun is actually right smack in the middle. Okay. Alpha Centauri A and Alpha Centauri B are also main sequence stars, and they're actually next door neighbors after Proxima. Okay. And then you have Proxima. Okay, they're all in the same line. Series A, which is a big star, also bright star in the night sky, is also a main sequence star. Series A and B are actually part of a binary star system. One of them is a main sequence star, another one is not. Actually, Series B is a very tiny white dwarf. Okay. So outside of the main sequence stars, you have things that live on above and things that live below. Things that live above, they're more luminous, brighter. Okay, depending on how far they are. Basically, the brightness depends on how far they are. Okay, luminosity, it doesn't matter. If you are right there, that's basically, if you put them side by side, the more luminous will shine brighter. Okay. Now you have the red giants in here. Look at, for example, Betelgeuse, extremely low temperature, but it's much more bright, super luminous star, meaning that it's extremely large. As a matter of fact, there is another measurement in here, and that measurement is this line in here that gives you how the radii is compared to the radius of the sun. Okay, again, we take that as 1. Anything below this line is small in size, so Alpha Centauri B is less in size than the sun, whereas Alpha Centauri A would be slightly more. Okay, That's base, but they're practically very close from the sun in terms of size. But Proxima b is extremely small. Okay, I mean Proxima Centauri is I'm sorry, is much less than the sun. Okay, so this is in terms of the characteristics of the stars. And then you have the white dwarfs. The white dwarfs are stars that basically died a long, long time ago. They consumed all of their hydrogen in their cores, and they ended up in here. So that's basically the graveyard for the low massive stars. But a more massive star will end up as a supergiant and then explodes. Okay, so at some point it's going to be a red giant. When it turns out of hydrogen, then it's going to become a consuming its helium. Then in that, because the temperature becomes so hot and denser, so in this case it's going to actually fuse helium itself, and then it's going to be a yellow giant, and then it's going to explode. And once it explodes, it's going to explode either in the remnant is going to be either a black hole if it's supermassive, or a neutron star if it's not that massive, but it's still bigger than the sun. So this is in a nutshell the answer to the question and to the life cycle of the star. So that's basically depending on its mass. So that is basically what the diagrams are. And as a matter of fact, there is a picture in here which shows you the life cycle and how the star goes through a full cycle in here when it's low massive, and it also goes through a full cycle when it's a massive star, with the exception that the remnant in here will be a neutron star, which is extremely small in size compared to a white dwarf or a black hole, depending on where you start from, which is going to be even probably smaller because of the high density in there. It's going to be a point actually in space. And for a low massive star, again, you're going to have the protostar. That's where it starts from before fusing hydrogen. Once it fuses hydrogen, it becomes a star, and it's a main sequence star. And then after that, it's going to, when it runs out of hydrogen in its core, is going to fuse the helium, and then it starts to, it's going to fuse the hydrogen in the outer shells, and then it's going to become bigger because of the extreme high rate that it's going to go. So it's going to overcome its gravity. So it increases in size and then consumes the hydrogen, because then it's got the temperature will it shrinks, sort of turns out of it, shrinks back in. So the temperature will increase higher, fusing more helium. And then after that, when it runs out of that, it's going to even expand at that point in this case, because of the, the rate increases further and further and increases in size. And as it turns out of basically hydrogen is going to then, the collapse will cause it to collapse further in this case into a point as small as possible until the forces of electrostatic forces and actually the nuclear forces prevent it from going any further. And because it does not have any much more mass, so it's going to stop at that point. Okay. And in this case, there is no nuclear reactions happening anymore. So it's going to be dying and getting its temperature, whatever it started with, and it's going to be cooling down until it basically becomes a dark, no energy whatsoever. Anyway, this is in a nutshell. Then you have the mass that is ejected, which is mainly hydrogen and helium, that is going to coalesce again and form another star. So this cycle repeats again. Similarly, in a similar fashion, with the exception, once you reach to this stage in here, you still have a lot of mass that is due to gravity is collapsing. And as it collapses further and further, so it's going to overcome those forces and here the repulsive forces until all of the basically protons convert to neutrons. So you end up with a neutron star, or even further than that, until there is no stopping to the collapse due to the force of gravity, and you end up with a black hole singularity. Okay. So this is in a nutshell. And then the remnants of the materials, the supernova material that comes out, again, it's going to coalesce and form another star. When it's a main sequence star, it's going to be hotter than a smaller size star. So this is in a nutshell the summary of those two questions. So I want you guys to read through the chapter, go through all of the details and all of these things, because you're going to be tested on this, on the materials in that. How a star evolves in the E chart diagram depending on its mass. If it's a low mass star, it's going to go through the red giant stage, then collapse a little, then increase its temperature, and then expand again because the high rate starts to increase until it overcomes gravity, and then it's going to evolve back into a white dwarf. And if it's a supermassive star, again, it's going to go through a violent explosion, and that's going to be a supernova, leaving at the end black hole or a neutron star. Now, it's important to understand that there is no physical migrations in this case. It's not like the star is moving somewhere in space like this. No, it's actually the same spot. I mean, it may be moving around the axis of the galaxy, but that's another problem. And it keeps on doing that, regardless of what's going on. But the HR diagram is just its position in terms of temperature and luminosity. That's all. It's still the same thing. When a star is supermassive, there is another chain reaction, or actually another process through which it's going to form high helium, other than the proton-proton nuclear reaction, and that is the CNO cycle. Carbon, nitrogen, oxygen basically cycle. They're still getting 4 protons to fuse to form helium in similar fashion, with the exception that this nuclear reaction has a catalyst now, and the catalysts are these 3 elements that are existing now, and they're being pushed inside and to fuse in this fashion. So since it's a cycle, you take it from any point you like, carbon-13, combining with a hydrogen proton, in this case, to form nitrogen-14. It went up from 1 proton extra to, to a nitrogen, which is from 6 to 7, 6 protons to 7 protons, because it captured this proton. And then from 7 to 8, that's an oxygen. And each time the number of nucleons increases from 13 to 14 to 15 now. So this is not the normal isotope of oxygen. Oxygen normally is 16. So this oxygen is 15. It has 1 less proton, 1 less neutron than what it should really have. Okay, so one of those neutrons, as a matter of fact, one of those protons is going to decay and go back into a nitrogen. Okay, now we have nitrogen 15, and the decay again produces a neutrino. Okay, plus a positron, which is cancelled by an electron. Again, you're going to capture another proton in this case and go through from nitrogen 15 to carbon 12 and ejecting 4 nucleons in the process. Remember, it captured 1, so it's 16. 16 plus 15 plus 1 is 16, minus 4, so you end up to 12. This is a normal carbon. Okay, the normal carbon now will capture a proton. So this is the production of the helium, this stage. So you capture another helium, and then you go another hydrogen, I'm sorry, another proton, and go into the nitrogen 13, which produces again another neutrino. So in terms of the production, it's similar in fashion to the proton-proton reaction, except that this CNO cycle now requires these 3 elements as catalysts, namely carbon and nitrogen and oxygen, and produces the same amount of helium in this situation. Okay. In terms of calculations, I mentioned before, and I don't know if I mentioned the first calculation and how it goes about. This calculation here in terms of the luminosity. Luminosity is proportional to the mass of the star to the power 3.5. Not to the power 3, not to cubic power, not to the power 4, but somewhere in between them. So if you have scientific calculator, easy to do this calculation. If not, think of it as a to the power 7, but take the square root. So take the mass, multiply it by itself 7 times, and divide this, take the square root at the end. So if you don't have that calculator that takes to the power 3.5, that's what you get to do, okay? When you double the mass, for example, it's very important to understand what's going to happen to the luminosity. It doesn't double, it goes more than that. Let's think about it. Because when you double the mass, you're going to take 2 to the power 3.5. Well, 2 to the power 3 is 8 already, because 2 times 2 times 2 is 8. And times the square root of 2, because 0.5 is square root, times square root of 2, which is 1.4. 8 times 1.4 is anywhere around 11. Okay, so you can do an exact calculation with it and you will find the number. It doesn't matter. It's more than 10 times. So the luminosity increases. If you double the mass, the luminosity goes by a factor more than 10. It's a big number. Okay, so it's important to understand what's going on in here. Which brings me to the other formula in here in the calculation, that is a lifetime of a star. The lifetime of a star is the ratio of its mass divided by its luminosity times 10. Okay, a word about the units. Obviously, this relationship is proportional if you use the proper units, kilogram for mass and luminosity, which has the proper units in SI, or used as compared to that of the sun. Then in this case becomes unitless. Okay, same thing in here. If you use this formula in the case of the mass of the sun and the luminosity of the sun as being 1, so in this case, you're going to find the time how long the star will live. So if you double the mass, for example, we just saw that the luminosity will go by a factor of by 10. So a star that is twice as massive will live 1/10 the life of a star of a sun. So the sun, M, which is 1, L, which is 1, 1 over 1 is 1 times 10 to the power 10, it's 10 to the power 10. So it's 10 billion years the sun will live. Whereas a star that is twice as massive, like for example, Series A, then in this case, the luminosity will be 10 times, and 10 to the power 10 divided by 10 to the power 10 is going 10 to the power 10 divided by 10 is actually going to be 10 to the power 9. And 10 to the power 9 is a billion years. So something like Series A will live about a billion years, which is 1/10 the life of a sun. If you take a star that is, for example, Proxima Centauri, I'm sorry, which is a lot less massive than the sun, which is a lot less luminous than the sun, because remember the same law also will work backward. So if you take the mass and you divide it by 2, half the mass of the sun, the luminosity will drop by a factor of 10. It doesn't go by factor by anything, so it goes a lot less. So again, star like this one will live for hundreds of billions of years. Remember, the universe is only 13 billion years. So those stars, some of them existed from the time when the universe exists until now. They're extremely young, and they will go in for a long time after the sun is gone and so many big stars are gone. So this is in a nutshell what these expressions are. The last point in here about the convective zone, which is a process with which stars lose energy, which is really the motion of the fluids in there, the gases, which is mainly hydrogen and helium. Again, for a low mass star, the convective zone extends all the way to the core, which means that the convective zone is responsible for recycling and putting more hydrogen into the core, getting it more reactive in there and helping the star go longer, stay longer. So this formula is an approximative formula. Same thing with the first one in there. They are not, and they work mainly for the main sequence stars. Okay. For a main sequence star like the sun, for example, the convective zone in here is very far away from the core, so it does not mix hydrogen into the core. So the core, when it runs out of hydrogen, it runs out of hydrogen. It's not going to get this hydrogen into it and start fusing it. That's it. That's why it needs other processes for it to continue, but that's basically the end of it. For a more massive star, the extreme high temperatures in there will cause this convective zone to exist in there, which enables it to fuse more and more of the hydrogen in there. And remember, we just mentioned the CNO cycle in there, which is another process with which the star can actually get that hydrogen to fuse. Anyway, so this is in a nutshell the introduction to this chapter. Okay, there's 3 units. And also the main thing in here is that please take care of that survey, and very important to prepare for your midterm next week. There is no homework this week, at least for this units. There is no quiz for this week because again, we have an exam. Thank you.